Okay, so we've got this stack of articles all about quantum computing.
Mm-hmm.
Specifically, Google's new Willow chip.
Mm-hmm.
You want the inside scoop on what makes Willow so special. Why it's causing such a stir.
Yeah, it really is.
There's a lot to unpack.
Yeah, it is. It's like stepping into a whole new dimension of computing.
Right.
Quantum computing uses these crazy rules of quantum mechanics to process information in ways that our everyday classical computers just, they can't.
Right. And these articles are full of terms that we're starting to hear more and more. Qubits, superposition, entanglement.
Yeah.
They're kind of central to this whole thing, right?
You're exactly right. Those are the keys to understanding what makes quantum computing so powerful.
Okay.
So let's start with a qubit. Think of it like the bits in a classical computer, like a 0 or a 1.
Okay.
But a qubit has this twist.
Okay.
It can be in a state of what we call superposition,
Okay.
which means it can be both 0 and 1 at the same time.
Whoa. So it's not just an on or off switch.
No, not at all. It can be both. And that's where things start to get really interesting, because now you have this single qubit that can explore multiple possibilities all at once.
So does that mean that a quantum computer can run tons of calculations all at the same time?
Yeah, exactly. It's like having this massive parallel processing system.
Yeah.
And that's what gives quantum computers the potential to just blow classical computers out of the water for certain tasks, for certain very specific types of problems.
Wow. Okay, so we've talked about qubits and superposition.
Yeah.
Now what about this thing I keep hearing about called entanglement? It sounds like something out of Star Trek.
Yeah, it kind of is. Like it's mind-boggling. So entanglement is when you have two qubits.
Okay.
And they get linked together.
Okay.
In this way that they act like a single unit.
Okay.
Even if they're physically miles apart.
Really?
Yeah. So if you measure the state of one qubit, you instantly know the state of the other one.
That's wild. It's like they're talking to each other, like telepathy or something. So one of the articles mentioned that Willow solved a problem in 5 minutes. That would have taken a classical supercomputer like 10 septillion years. Is that even possible?
It is, but it's important to remember that this particular problem was specifically designed to play to Willow's strengths. Quantum computers, they're not meant to just replace classical computers altogether. They're more like specialized tools for very specific jobs.
Okay, so that makes sense. You wouldn't use a scalpel to chop down a tree.
Exactly.
So what is it about Willow that makes it so groundbreaking? What's the secret sauce?
Well, there are a few key things. First, Google's engineers have managed to achieve a remarkable level of what we call qubit stability.
Okay.
So the design and the materials that they're using for Willow allow these qubits to maintain their quantum states for much longer than previous attempts, and that reduces errors, which is huge.
So it's like they've created this perfect little environment where those spinning coins
Mm-hmm.
can stay balanced for a really long time.
Exactly. Yeah, that's a great way to think about it. Another thing is their error correction. So they've implemented these really sophisticated error correction codes that act like a kind of quantum spell checker, constantly monitoring and fixing any errors that creep into those calculations.
Wow. So it's like a built-in quality control system for the quantum world. That's pretty impressive.
Yeah, it is. It's really impressive. And finally, Willow's chip architecture. The way it's laid out, it's specifically optimized to reduce interference between the qubits.
Okay.
And that leads to cleaner, much more accurate computations.
So it's like they've created a quantum-friendly environment on the chip itself.
Yeah, exactly.
You know, I was reading about these qubits, and I have to admit, I got a little hung up on whether a qubit is a physical thing
Yeah.
or just a concept. It seems like it's kind of both.
Yeah, you've hit on something really important there.
Okay.
A qubit, it is both. It's the fundamental unit of information in a quantum computer, just like a bit is in classical computing, but it's also a physical device. So in the case of Willow, they're using these things called superconducting circuits to create these qubits.
Okay.
So it's kind of like you were saying, you know, you have a light switch.
Yeah.
That represents the concept of on and off, but it's also a physical object
Right.
that you can interact with.
Right. You can flip it.
Exactly.
Okay. That makes sense. One more thing that I was wondering about. The articles mention this idea of infinite superposition states. Does that mean that a single qubit can store an infinite amount of data?
Theoretically, yes. You can think of a qubit state as a point on a sphere.
Okay.
Each point on that sphere represents a different superposition, but in reality, there are limitations.
Okay.
You know, we have noise, we have errors, And we have the limits of our control systems. So we're not quite at the point where we can cram infinite data into a single qubit.
Okay. So infinite possibilities in theory, but real-world limits keep us grounded.
Yeah, exactly.
Okay. All of this is incredible, but it also sounds incredibly complex and expensive.
It is.
So how does Willow's energy, use, and cost compare to something like a supercomputer?
That's a really good question. And it's something that a lot of researchers are thinking about right now. It's like comparing, you have a race car and you have a really heavy-duty truck. They're both powerful, but they're designed for very different things.
So where does quantum computing fit in? And we already have supercomputers.
Right.
What's the advantage? Why should we even invest in quantum computing when conventional computers are already so powerful?
Yeah, that's a great point. So even though our classical computers are incredibly powerful, there are certain problems that no matter how much we improve them, they just can't solve efficiently.
Yep.
And that's where quantum computing comes in.
Yeah.
It's not necessarily about replacing classical computing altogether, but it's about tackling those problems that are just beyond the reach of even our most advanced supercomputers.
Okay. So it's like having a specialized tool for a very specific job. You wouldn't use a sledgehammer to crack a walnut.
Exactly.
Okay. So what are some examples of these, quantum advantage problems that classical computers struggle with?
So one of the most famous examples is breaking encryption. So a lot of our online security systems rely on the difficulty of factoring large numbers, which is a task that classical computers find incredibly difficult and time-consuming. But a quantum computer, using something called Shor's algorithm, could potentially crack those codes in a fraction of the time.
Whoa.
Yeah.
It has huge implications.
Yeah, it does. Another very promising area is drug discovery and material science. So quantum computers could potentially allow us to simulate the behavior of molecules at a level of detail that's just impossible with classical computers right now.
So instead of having to rely on these approximations or models, we could actually simulate those quantum interactions happening at the molecular level.
Exactly. And this could revolutionize the way we design new drugs, new materials, and lead to all sorts of breakthroughs in medicine, energy, manufacturing, who knows what else.
Yeah, that's pretty amazing.
Yeah.
You mentioned that classical computing systems are being improved all the time.
Yeah.
Are there ways to make them more competitive with quantum computers, at least for these specific tasks?
Yeah, absolutely. So there are a lot of really smart people working on pushing the boundaries of classical computing, especially in areas where quantum computers show promise.
Okay.
So one approach is to develop what are called specialized hardware accelerators.
Okay.
Things like ASICs, FPGAs, GPUs. These are designed to perform very specific types of calculations, much faster than general-purpose processors.
So it's like giving our regular computers some quantum-inspired upgrades.
Yeah, you could think of it that way. Another exciting area is neuromorphic computing, which is about building computers that mimic the structure and function of the human brain.
Oh, wow. So we're trying to replicate the brain's processing power, but using conventional hardware.
Exactly, yeah. And of course, there's always room for improvement in algorithms and software by developing more efficient algorithms and optimizing code. We can often squeeze out more performance from our existing hardware.
Right.
And we can also explore what are called hybrid quantum classical algorithms. So we combine the strengths of both, using quantum computers for the parts where they excel and classical computers for the parts where they're more efficient.
So it's really a collaborative approach, using the best of both worlds.
Exactly, yeah. It's not necessarily a battle between quantum and classical, but more about finding the right tool for the job.
Okay, that makes sense. What about efforts to make these conventional computers more energy efficient? Yeah. Especially for these really large-scale computations.
Yeah, that's a huge area of research. So energy efficiency is a major focus in computer science these days, especially as we're building these larger and more powerful systems. So there's a lot of work being done on developing low-power architectures, more efficient cooling systems to reduce the energy footprint of these supercomputers.
So it's not just about raw power anymore. It's about making those computations more sustainable.
Yeah, exactly. And then there are some really out there approaches like analog computing and optical computing. which use different physical principles for computation.
Right.
And could offer even greater energy efficiency.
Analog and optical computing. So what are those?
So analog computing uses continuous signals instead of these discrete bits, which can be more efficient for certain types of problems. And optical computing uses light instead of electricity, which has the potential to be incredibly fast and very low energy.
Wow. It sounds like the future of computing is going to be very interesting with all these different approaches.
Yeah, it is. It's an exciting time to be in this field.
Okay, so with all these efforts to improve conventional computing, why should we even bother with quantum? I mean, it seems like kind of a risky bet.
Yeah. It's true that quantum computing is still in its early stages, and there are many challenges ahead, but the potential payoff is just enormous. There are certain problems that classical computers just fundamentally cannot solve efficiently, no matter how much we improve them. And quantum computers offer this completely new way of approaching computation.
Yeah.
That could lead to some really groundbreaking discoveries.
So it's not just about doing things faster. It's about doing things that are currently impossible.
Exactly.
Wow. So even though conventional computing is evolving rapidly, there's still a strong case to be made for investing in quantum because it offers this whole different paradigm. That could open up new frontiers in science and technology.
Absolutely. Yeah, it's about expanding our computational horizons.
Yeah, I like that. It's not just building faster computers.
Right.
It's building computers that can do things that we can't even imagine right now.
Yeah, exactly. It's about unlocking this whole new level of understanding and innovation.
Well, you've definitely given me a lot to think about.
Good.
It seems like the future of computing is going to be this really interesting mix of quantum and classical technology.
Yeah.
Each one kind of playing to its strengths and pushing the boundaries of what's possible.
I agree. Yeah. It's an exciting time to be following the evolution of computing.
We were talking about the future of computing and how quantum and classical computing will work together. And I keep thinking about this idea of quantum supremacy. What does that even mean? What's the big deal?
So quantum supremacy, or quantum advantage as it's sometimes called, is basically that moment when a quantum computer can solve a problem that's essentially impossible for even the most powerful classical computer to solve in any reasonable amount of time.
So it's not just about speed. It's about being able to do things that are just completely out of reach for our current computers.
Exactly. Yeah. It signals this fundamental shift in our computational abilities. And Google actually claimed to have achieved quantum supremacy a few years ago.
Right, with their Sycamore processor back in 2019.
Yeah, exactly. So they created this very specific problem that their Sycamore processor was able to solve in just a few minutes, while it would have taken a classical supercomputer thousands of years.
Thousands of years?
Yeah. But there has been some debate in the scientific community about whether Google truly achieved quantum supremacy.
So are some researchers saying, hold on, maybe there's a better classical algorithm out there that could solve this problem faster?
Yeah, exactly. It's like this constant back and forth, you know?
Right.
The field is moving so quickly that what might be considered a quantum advantage today could be within reach of classical computers tomorrow.
Right. It's a really interesting race.
It is. It's fascinating.
So you wonder what problems will be considered quantum supremacy worthy in a few years.
Yeah, definitely.
Okay. We've covered a lot of ground here, from the basics of quantum mechanics to the potential of these quantum computers like Google's Willow. But I want to touch on one more thing that I found really intriguing in these articles. And that's this idea using quantum computers for artificial intelligence.
Quantum AI. Yeah, that's a really hot topic right now. So at its core, AI is all about algorithms that can learn from data and make decisions. And it turns out that quantum computers might be able to supercharge those algorithms.
So we're giving AI a quantum upgrade.
In a way, yeah.
Okay, so how would that work?
Well, one way is by speeding up the training process for machine learning models. So these models often need to crunch through massive amounts of data, which can take a really long time, even on powerful computers.
Yeah.
But quantum algorithms could potentially speed up those calculations dramatically, leading to more powerful and sophisticated AI systems.
So it's like fast-forwarding the learning process for AI.
Exactly, yeah. And it's not just about speed. Quantum computers could also enable us to create completely new types of AI algorithms that are inspired by quantum mechanics.
Quantum-inspired AI algorithms. What could those algorithms do that today's AI can't?
Well, that's still an active area of research. But some experts believe that these new algorithms could be really good at things like pattern recognition, optimization, handling uncertainty, which are all really important for many AI applications.
So we're talking about combining the power of quantum computing with the flexibility and adaptability of AI.
Exactly.
It's a pretty powerful combination.
It is.
Okay, so how do people actually work with a quantum computer, like the Willow chip?
Right. So it's not like you just boot up your laptop and start coding.
No.
No.
Oh.
Accessing a quantum computer like Willow usually involves using a cloud-based interface.
So you're essentially accessing a really powerful server remotely.
Exactly, yeah.
Okay. What are some of the challenges of actually programming one of these quantum computers?
Right. So quantum programming is a whole different beast compared to classical programming. One of the biggest challenges is dealing with the inherent uncertainty of quantum systems.
Okay.
You can't just give a quantum computer a set of instructions and expect a predictable outcome every single time.
So it's not deterministic.
Exactly. So with superposition and entanglement, we're dealing with probabilities, not deterministic outcomes. So you need to think about computation in a much more statistical way.
Okay.
There are also challenges in managing entanglement and minimizing errors, which require special techniques and algorithms.
It sounds like quantum programming requires this deep understanding of both physics and computer science.
Yeah, absolutely. It's a very interdisciplinary field.
So if someone wanted to dive into this world, where would you recommend they start?
Well, the good news is there are more and more resources becoming available to learn quantum programming. There are open source quantum programming libraries, online tutorials, and even quantum computing simulators, which let you experiment with these quantum algorithms without needing access to an actual quantum computer.
Oh, so I don't have to build my own quantum computer in my basement.
Not yet, anyway. Who knows what the future holds?
That's true. So we've talked about the potential of quantum computing in medicine, AI. But what about its impact on society as a whole? How do you see quantum computing changing our lives in the years to come?
That's a big question. So as quantum computing becomes more powerful and more accessible, it has the potential to impact many aspects of our lives. Everything from finance to logistics, even education and research. Imagine a world where scientific discoveries are accelerated by quantum computers, or personalized medicine is commonplace.
Yeah, it's mind-boggling. But it also brings up some ethical questions. We need to be careful about how we develop and use this technology.
Absolutely. Like any powerful technology, it can be used for good or bad. So it's essential to think about the ethical implications of quantum computing and to develop guidelines to ensure that it's used responsibly for the benefit of humanity.
Well, this has been a really incredible deep dive.
It has.
It feels like we've only just scratched the surface of what quantum computing can do.
I agree. There's so much more to explore.
It's a good reminder that we're living in this time of incredible technological progress. Who knows what breakthroughs are just around the corner?
Yeah. The future of quantum computing is full of unknowns, but that's what makes it so exciting.
On that note, I think it's time to wrap up our deep dive. Thanks for joining us on this journey into the quantum world.
It's been a pleasure.
And to our listener, if this deep dive has sparked your curiosity about quantum computing, don't stop here. Keep learning, keep exploring, and who knows, maybe you'll be the one to make the next big breakthrough in this amazing field.